Hello and welcome to our lesson on geometric sequences. Today, we will explore an essential area of algebra that will help you recognize patterns and solve problems with greater confidence. In this lesson, we will build upon our understanding of sequences and delve into the specifics of geometric sequences. We'll begin by learning how to identify a geometric sequence. Next, we'll discuss how to extend these sequences by finding their next terms. After that, we'll apply our new knowledge to various examples to solidify our understanding. Introducing today's concept of geometric sequences allows us to uncover patterns where each term after the first is found by multiplying the previous term by a constant called the common ratio. Let's get started. In our last lesson, we learnt about arithmetic sequences, those sequences in which each term increases by a constant amount. For instance, in the sequence 1, 3, 5, 7, each term is obtained by adding 2 to the previous term. So we could describe this sequence with the nth term formula 2n plus a, where 2 is the common difference, and a equals minus 1, which can be found by plugging n equals 1 into the formula and equating it to 1. The formula becomes 2 times 1 plus a equals 1. When rearranged to find a, the formula is a equals 1 minus 2 equals negative 1. Now let's transition to geometric sequences. What do you think is happening in the sequence 2, 4, 8, 16? How would you generate the next term? In this sequence, each term is found by multiplying the previous term by a constant value. This kind of sequence is called a geometric sequence. The constant value we multiply by is known as the common ratio. Here are more examples of geometric sequences. The sequence 3, 6, 12, 24 is geometric because each term is multiplied by 2 to get the next term. So is the sequence 5, 10, 20, 40. To describe a geometric sequence mathematically, we use the form AR squared, etc., where AR is the first term and R is the common ratio. Let's use an example to demonstrate how to work out the value of any term in the sequence. Say we have a geometric sequence where the first term A is 2 and the common ratio R is also 2. To find any term, we use the formula. The first term is I equals 2. The second term is AI equals 2 times 2 equals 4. The third term is AR squared equals 2 times 2 squared equals 8. The fourth term is AR cubed equals 2 times 2 cubed equals 16. Next, let's discuss how we can use trial and error to find rules for sequences. If a sequence doesn't seem to be linear, it might be geometric. For example, if the first term is AR and the second is AR squared, we can use the information we have about rearranging equations to find the common ratio. We'll dive deeper into this in later lessons. Let's compare geometric and linear sequences. Geometric sequences grow much faster because the distance between each term increases exponentially, whereas in a linear sequence, the difference between terms is constant. This difference can help you remember which is which. To illustrate this, consider the sequences on the right. Which one is geometric and which one is linear? The sequence 4, 7, 10, 13, and 16 is linear because it has a constant increase of 3. The sequence 5, 10, 20, 40, and 80 is geometric because each term is multiplied by 2. For the linear sequence, we can quickly identify the nth term rule. For the geometric sequence, we can identify the following pattern. The first term 5 is a bracketer to the power of 0, which means a equals 5. The second term 10 is a bracketer to the power of 1. So 10 equals 5r, which gives us r equals 2. Note that a geometric sequence does not have to be increasing. For example, the sequence on the right is a decreasing geometric sequence with a common ratio of 1/2. By recognizing these patterns, you can practice finding the next terms in sequences and constructing the formulas that describe them. Let's try out some problems to test what we've learned about geometric sequences. Picture this. You're playing a game of chess. and you're curious about the number of grains of wheat you'd have if, starting with 1 grain on the first square, you doubled the number on each subsequent square of the 64-square chessboard. This is an example of a geometric sequence in real life. Here's how to work it. Firstly, identify your sequence. Let's list down the first few terms. We've got 1, 2, 4, 8, each term obtained by doubling the one before it. Then identify the common ratio. Since a geometric sequence involves multiplying by a consistent number from one term to the next, we need to identify this number. The common ratio in our sequence would be 2 because we double each preceding term. To find the next few terms, we apply this common ratio by multiplying the latest term by 2. So if we were to continue the sequence after 8, we'd have 16, then 32, then 64, and so on. On a chessboard, multiplying by 2 moves you to the next square, so to find out how many grains you'll have on the 64th square, well, that will be quite a large number. Remember, what we've just learned isn't only applicable to a chess game, but to many real-world contexts. For instance, think about a population of bacteria that doubles every hour. Now I want you to try identifying the common ratio and finding the next few terms of these sequences: 5, 10, 20 and 40, and 3, 9 and 27. The first sequence's common ratio is 2, as we multiply each term by 2 to find the next. Therefore, the next term in this sequence would be 80 followed by 160. The second sequence's common ratio is 3, as each term is multiplied by 3 to find the next. The next term in this sequence would be 81. Great job on taking this concept and applying it to real-life scenarios. In today's lesson, we began by identifying the characteristics of geometric sequences, where each term is obtained by multiplying the previous term by a constant value known as the common ratio. We looked at examples such as 3, 6, 12, 24, and 5, 10, 20, 40, noting that these sequences grow exponentially compared to linear sequences, which increase by a constant amount. We also discussed the mathematical representation of geometric sequences using the form AR squared, and so on, where A is the first term and R is the common ratio. Through examples, we demonstrated how to find any term in a geometric sequence using this formula. Additionally, we compared geometric sequences with linear sequences, emphasizing their differences in growth patterns. Overall, today's lesson has enhanced your ability to work with sequences by focusing on the specific properties of geometric sequences. Watch the rest of the GCSE Maths course at Sophos Education.